But good morning. Thank you so much for joining us today. As Andrew said, my name is Liz Moore, and I'm joined by Dr. Marcos Miranda from Carbon Solutions. And we're very excited to share our work today on understanding carbon capture utilization and storage, or CCUS strategies, for hard-to-abate industries, including the cement, steel, and petrochemical sectors. Our research team at the MIT CS Hub has been working to accelerate decarbonization in the cement and concrete industry since about 2009. We believe there are important decarbonization actions that need to occur throughout the value chain, and we do our best to research strategies from a systems sustainability perspective. In reviewing different hard-to-abate industry carbon neutrality roadmaps, such as the PCA roadmap, we know that CCUS will be required to fully decarbonize by mid-century, particularly for those hard-to-abate industries like cement, steel, and petrochemicals. There are new companies pioneering low-carbon innovations, such as those re-engineering the cement production process. However, to meet climate goals at the speed and scale that's required, these solutions need to be rapidly deployed. This can take time to move from the pilot to commercial scale. As many of you know, there are engineering refinements, high investment required, regulatory barriers, and many more. While CCS still faces some barriers, we believe that it will play a key role in achieving timely decarbonization goals. The capture technology is a significant portion of the overall cost, and this is where we see the most support or incentives. However, for deployment at scale, the build-out of a pipeline network will be needed since not all of the locations are co-located with suitable deep geologic storage. Over the past few years, several studies have analyzed optimized CCUS pipeline infrastructure design. However, we believe these studies do not address some realistic constraints. Many of these studies assume that all locations and industries have the same motivation to participate and assume that the lowest cost industries will deploy CCUS first. But in reality, we've observed that there's a broad range of pressure on these different industries to participate, with the greatest pressure on the hard-to-abate industries. After power generation and fuels, the cement, steel, and chemicals industries, as you can see here, are some of the highest emitting and most difficult to decarbonize industries, and all three have significant pressure to decarbonize. Despite the industry's motivation to decarbonize and deploy these technologies, there are still significant barriers. We believe that there are two strategies that could really help to enable broader decarbonization across the US. One, investments in hard-to-abate industries as first movers, and two, the formation of carbon hubs around these industries. In this study, we begin to investigate the implications of moving forward with a CCUS system focused on hard-to-abate industries as first movers. We are investigating the following research questions using spatial-economic systems analysis. For different levels of industry abatement, what would be the length, size, and cost of a pipeline network, capture installations, and storage systems? Can strategically designed industrial carbon hubs accelerate widespread CCUS adoption? To what extent could these hubs really increase the emissions captured? How cost-effective could this be? What are some of the barriers to industry participation? I'm going to first pass it over to Marcos to talk about our partner in this work, Carbon Solutions, and a description of the tools that they've developed, some of which were used in designing the system that we'll talk about today.
Thanks, Liz. So my name is Marcus Miranda. I'm a research scientist at Carbon Solutions. And just to kind of dive straight on in and give a little bit of background, the real motivation of Carbon Solutions is to work with industry to deliver energy solutions that are better, faster, and cheaper, realistically. Carbon Solutions was launched back in 2021. We now have around 27 employees, and we've had over 100 different projects over the years. Most of our funding right now comes from the government, but the remaining is split pretty evenly between NGOs and industry as well. And the foundation really of Carbon Solutions was the development of SimCCS, or SimCCS Pro as we call it now, which I will be talking about in a little bit, which is our CCUS CCS software. Really looking at focusing at Carbon Solutions at energy applications, whether it's related to the CCS space, working with people like Liz, or if it's looking at hydrogen, geothermal, energy storage, grid modeling. And we do this using software related to a lot of different tools, looking at CCS as well as hydrogen, geothermal, methane detection, and air quality. So there's a lot of different software and tool sets at Carbon Solutions to kind of help us with these energy applications. And we do this using optimization, reservoir simulation, life cycle assessment, looking at techno-economic assessment, as well as GIS and machine learning. Next slide, please. Thank you. So this is the main set of software suite that we used in this project, working with Liz and the folks over there at MIT. So SimCCS Pro provides our system analysis. So it's kind of decision support across the CCUS value chain. We have Concord, which is deals with capture. It's a dynamic, customizable facility software and database that has over 10,000 different sources. You have CostMap Pro, which handles the transport side of things, thinking about pipeline routing, transmission line routing, as well as different types of different types of transportation. And then you have Scott Pro, which handles storage. It's the most advanced and accurate tool for dynamic CO2 storage potential and cost as well. And I'm going to go into a little bit of detail about each of these next. Next slide, please. Thank you. So Concord stands for the CO2 National Capture Opportunities and Readiness Database. It's basically looking at, it's an industry facility software database for different processes, fuels, and emissions. So the main motivation behind this was to be able to quickly categorize and characterize different individual CO2 sources, as well as determine what kind of emissions and potential capture costs come from capturing CO2 at those locations. And we also wanted to be able to provide a kind of a directory of CO2 opportunities for different interest parties, looking at, hey, what's going on around us? What are the different opportunities we have for capturing CO2? Who could we partner with locally? And this could be really important for hard-to-abate sectors that are looking at trying to generate and bring in more interest from those facilities that are around them. And through this process, we've kind of figured some of the customers that we've discovered are different capture technologies, investors, CO2 customers. So you're thinking about people who could use captured CO2 emissions, as well as governments and NGOs. Next slide, please. Next, we have CostMap Pro. So this is the most advanced pipeline and transmission routing tool. So what you're seeing on the right now is a cost surface, just like an average cost surface for the entire United States, showing what is kind of how it looks visually, as we're taking into account a lot of different factors in our pipeline routing and transmission line kind of analysis. So we want to be able to quickly identify different corridors that help balance the costs, the connectivity between where you're capturing CO2 and where you're storing it, as well as what the impacts are, and kind of be able to provide a detailed route analysis. What's going through where is your route going through? What's going on in those areas? What are the different factors that might impact the costs of that routing, that pipeline that way? And through this, we've kind of discovered different customers involving utilities, oil and gas, different CCS, whether it's users, people who want their CO2 captured, things like that, as well as, of course, governments and NGOs. Next slide, please. So this is Scott Pro. It's one of the most advanced screening level storage potential, storage costs databases. It's basically, the motivation behind this was to be able to capture these complex storage systems with kind of fast running models. And we wanted to be able to rapidly characterize individual reservoirs, whether that's using the best publicly available data that's out there, or again, for a specific project, if you have specific reservoir characterization that people want to use, we're able to do that as well using the same models, being able to provide a more custom guess at looking at storage potential as well as storage costs. And so on the right, you're seeing kind of the extent of some of the publicly available data, as well as the storage potential for those locations across the United States. And Scott also provides information such as the storage costs associated with injecting CO2 at these locations as well. And through this, we've kind of discovered customers in the oil and gas field, different CCUS companies, again, EPC firms, as well as governments and NGOs. Next slide, please. So this is SimCCS Pro, which I talked about in the first slide. The outputs from all the different models and tools that I've talked about, so Concord, CostMap, Scott, all of those feed into SimCCS Pro. It is our CCUS infrastructure assessment tool that basically tells us where, how, and when to build this infrastructure. It doesn't have to be specific to CO2. It can be done as well for hydrogen, as well as other fuels or resources as well. On the capture side, we're looking at the CO2 emissions. What are the capturable amounts of CO2? The streams, what are the economics? So there's capture costs, as well as what are potential co-benefits from capturing or avoiding those CO2 emissions being released into the atmosphere. On the transport side of things, we're looking at pipelines and transmission lines, the routes, the economics. So you're looking at pipeline diameters, the length of those pipelines, as well as the unit cost for transporting the captured CO2 via those pipelines. And on the storage side of things, you're looking at, again, what I've talked about, that storage potential, looking at potentially using enhanced recovery or production, as well as geothermal, and then those economics, the unit level storage costs for injecting CO2 in a selected location. On the right, what you're seeing is different SimCCS Pro results, basically scaling the amount of CO2 we're capturing for an example in the Southeast US. And you can see in red, the sources that are being selected from, in green, the pipeline routes, in blue, the storage locations and how much potential is being used up for each of the different scenarios. We can see how this pipeline routing kind of evolves over time as we increase the amount of CO2 we're capturing. And this is kind of what we did working with Liz here on this project. And to tie all of this back in a little bit more specific to what we're talking about here, we used pretty standard default assumptions for Scott Pro and for CostMap on this project. But Liz, if you could go to the next slide. For Concord, we were able to work with Liz and identify 266 unique facilities across the 3 different industries we were interested in. So that was cement, petrochemicals, and then iron and steel. So the map on the right you're seeing is the location of all these different facilities, the different industries, as well as the capturable CO2 emissions. And so we were able to discover there's over 116 million tons per year of capturable CO2 emissions across all 3 of these industries and all these facilities. And so this is where we can kind of take our tools and make it more specific to the project or the interests that we have. And so with that, I will pass it back on over to Liz to kind of go over the results and talk a little bit more.
Thank you so much, Marcos, for explaining the suite of the tools. I'm going to take over now just to discuss a little bit more on some of the underlying methods used in this project. So we were able to feed in a lot of the work from the SimCCS Pro tools that Marcos just showed, but we did do a little bit more detailed capture cost modeling for the cement sector, as well as we started thinking about methods for how might we form carbon hubs. We noticed when reviewing the literature in detail that there were a lot of inconsistencies in the cement capture cost estimates. So we started by building out a capture cost model to mirror the capabilities of the NETL industrial CO2 capture retrofit cost model, it's a mouthful, and used individual cement plant data from the EPA flight database to estimate a range of the capture costs from amine-based capture technology. While studies have estimated capture costs for cement facilities in the past, the model that we've built accounts for variation in key parameters across facilities, including facility scale, the presence of pretreatment SOx and NOx technologies, air and leakage at the plant, and different fuel types. A next step for this work will be to investigate other types of capture technology, such as oxyfuel and cryogenic in greater depth, as well as capture costs for steel and chemicals. But our main cost modeling that we'll talk about today is for cement and amine-based technology. Once the capture, transport, and storage system is designed for our 3 hard-to-abate industries, we also use some spatial modeling to perform a nearest neighbor spatial analysis to identify some of the other industrial facilities that are closest to the hard-to-abate industry pipeline. for the formation of carbon hubs, and we identified a distance within 50 kilometers. In the picture that you can see here on the right, there's an example of a hub of purple point sources, a blue pipeline, which is this hard-to-abate pipeline, and dotted lines that are the potential hub connections to the pipeline. We know in reality these are not straight line connections, and so what we did was applied a detour index from the literature to account for how that pipe might actually be connected considering geography, etc. A next step for this work will be to use some of these distances to estimate from a GIS analysis the investment potential for carbon hubs. All right, now we are going to jump into some results. So before getting into the design for the three industries, we wanted to share the cost modeling results just for the cement industry, where we saw that significant cost variation in the literature. The median cement plant across the US produces about 878,000 tons per year of cement. We've estimated that the at-plant cost of capture, or the cost associated with separating a CO2 stream that is ready for pipeline transport, so that's going to include your compression, auxiliary equipment, and CO2 capture system, is at about $160 per ton of CO2. This is significantly higher than the estimate in literature studies of $69 per ton CO2, and even estimates reported for an average plant by NETL in the range of $105 per ton CO2. On the right-hand side here, you can see the cost broken down by total as spent capital, or the amount of money spent on the project over time, the raw total payments as they happen, fixed and variable operating costs, including labor, property taxes, insurance, water, and materials for the capture system, as well as the fuel and power costs. This is the median result, but we've also calculated this for every cement plant in the US. I also want to note here, we have taken these results and interviewed multiple cement companies to show our assumptions for this modeling, and many of the companies have confirmed that the assumptions are in line with what they would expect. I'm happy to share the documentation around the assumptions or the methods that we've generated with anyone. Please just feel free to reach out over email. In this slide here, the plot on the right-hand side, in the bottom right-hand, you will see that there are different blue bars. Each blue bar here represents an individual cement facility, and the length of those bars represents the possible cost range when you account for variation in the key parameters that I mentioned below, such as the pretreatment technologies for SOx and NOx, air and leakage from a facility, lower CO2 qualities, and others. We randomly assigned these different characteristics and performed around 1,000 simulations to estimate a cost range for each facility. So the x-axis here, that's the amount of capturable CO2 per year, and the y is the cost of capture. You can see strong economies of scale really lead to high capture costs. Our estimated cost range for all of these facilities is around $100 to $418 per ton of CO2, which is, again, higher than other studies that we've seen that report the capture cost only. We think that this shows that current incentives need to be higher to support hard-to-abate industries like cement for this to really be possible. Under the current 45Q tax credit of $85 per ton, not a single industry would qualify for this. And this is only for the capture costs, so this doesn't even include the transport and storage piece. Our goal is to continue to try to communicate and show that these cost estimates, there's really a need here for higher incentives for hard-to-abate industries. Okay, now we're going to jump into more of the design of the network. The three-industry pipeline network that you see here was designed for different levels of abatement. So from 15% abatement of the three industries all the way to 100% abatement of the three industries that's shown in the top right graphs. Stepping through the pipeline network changes for a specific region in Texas, in the A through D images below here, In the maps, the purple dots represent hard-to-abate industries. The black line is representing the pipeline. The blue is kind of the new pipeline addition as we increase abatement, and the gray squares are the sink location. This network varies from about 612 kilometers at 15% abatement to 15,862 kilometers at 100% abatement. As higher fractions of the industry are captured, you see that the costs begin to rise due to higher transport costs from longer pipelines per unit captured and the use of more expensive storage formations. Although the transport costs for this 100% abatement case are almost 3 times that of the 15% case, pipeline transport still is the most cost-effective means, even when comparing to trucking. And I think this confirms what we've seen in the literature as well as some of the recent roads to removal reports. One strategy to decrease the cost and risk of pipeline infrastructure could be to form carbon hubs of nearby industries that could help share that cost. We recognize that there are certainly barriers to this type of solutions, such as varying levels of CO2 purity from different industries, a lot of different stakeholders involved, and potential public perception issues. However, in this case study, we wanted to just start to understand quantitatively what the potential for carbon hubs could be to increase the emissions captured while lowering overall cost per ton of CO2. In this slide, the locations for potential carbon hubs within 50 kilometers of hard-to-abate industries are shown for the 100% abatement scenario. The map in the right-hand corner, it's kind of showing this zoom in on a buffer zone of a network in Texas, where there's 5 nearby facilities that could be candidates to form a carbon hub with these hard-to-abate industries. In these diagrams, the hard-to-abate industries are in purple, and this orange-red shading is really showing some of these other enabled industries. I'm going to flip to my next slide very quickly, where we're showing here the carbon hub result from the previous slide, but now it's layered on top of the 13 US geologic basin zones. As you can see, there are a significant number of these hard-to-abate potential carbon hubs that fall within these zones. These zones are labeled with the red numbers, and the zone area is kind of in this light gray shading. This shows that we can begin to identify carbon hubs that would be most strategic based on a number of variables, including the potential amount of carbon that's captured, the most economical facilities, and proximity to these geologic basins, where we see key benefits, including access to existing infrastructure for extraction, transport, and storage. So in this analysis, we really tried to develop a quantitative assessment of the CCS system that would be needed to create carbon hubs around hard-to-abate industries as first movers. The next step of this work will be to estimate cost savings from forming carbon hubs. It's, I think, important to note here that to capture emissions beyond these industries, the pipeline network would have to be increased. We'll have to account for this when we're doing some of the cost modeling and adjust some of the costs based on new pipeline sizes. When we've applied this just for the cement case, we found that connecting into a carbon hub might not be economical for all facilities within a 50-kilometer radius. If a facility is small and at the edge of a region, the cost to build out that pipeline connection may just not be justifiable. We did find for the cement industry, as you kind of see in this right plot here, that if facilities are selected strategically, the carbon hub network could capture 5 times the amount of emissions for cement facilities alone, while only increasing the investment by about 2x. Beyond that 6x emissions point, you start to see here that the cost required rises significantly to capture those last emissions. We are continuing this effort for the next few months and continuing on in this project. And as part of that, we are in the process of conducting some semi-structured interviews with hard-to-abate industries to understand the willingness to join or likelihood of participating in a capture network. During these interviews, we're also exploring the perception and barriers to utilization technologies, such as mineralization or carbonation of slag for construction aggregates for roads and buildings. And the hope is really to understand how utilization technologies could also potentially play a role in carbon hubs. If there's any company on this call that would be interested in participating in an interview, please don't hesitate to reach out. Finally, we've noticed that CCS will require a large amount of energy. We are starting to investigate the amount of excess electricity that's required and how that will impact regional grids to understand if this large increase in demand is worth the amount of CO2 captured. I'm now going to pause. Just want to thank you all for joining today. Thank you all for your time and interest in this work. We're very happy to take questions, have some discussion, or share resources if you have any questions after the call. But thank you so much for your time. I'll just leave this slide here for a second with our email addresses, and welcome any conversation here.
Okay, wonderful. So as we wait for more questions to come in, I wanted to start off with a topic that might be of interest to you, Liz, because I know this is one of your research focuses. Can you talk to me a little bit about how building out these carbon hubs, what implications that would have for the workforce and what sort of upskilling would be needed?
That's a really interesting question. I think in order to deploy these systems at scale, you'll need to have a skilled workforce not only on site at the plants, but also a skilled workforce that's capable of the build out and maintenance and operation of the pipeline system as well as the storage system. So I think there will be a significant need to think about that workforce and start to do that sooner rather than later, before we need to really deploy these technologies at scale. And I think there's quite a bit of training that can happen. I think there's some knowledge that we already know from pipeline transport of natural gas, for example, that may be able to be applied, but some different safety considerations, for example, that might need to be considered when transporting CO2. But I think that there's a significant opportunity for development of a workforce here. Like I said, both at the plant, the pipeline, and storage site, and even utilization technologies. I left those out. So thank you for that. It's very interesting.
Yeah, certainly. I guess let me see. One clarifying question. So could you clarify whether the pipelines are autonomous or whether they would be combined with existing or other industry pipelines? So maybe this is an opportunity to kind of drill down on the carbon hubs aspect.
Sure. Marcus, I want to make sure that I give you opportunity to answer too. Would you like to comment just a little bit about the pipeline build out using the Carbon Solutions tool and whether or not existing infrastructure is taken advantage of there, and then any thoughts you may have on the formation of carbon hubs, and I'm happy to add too.
Sure. Yeah. Happy to kind of help out a little bit here. So at least from the Carbon Solutions perspective, looking at cost map and the CCUS Pro tool, we do account for existing rights of way, whether they be transmission lines, pipelines, essentially what I was talking about with those corridors where it might be a little bit easier for routing a pipeline. So that is definitely factored into the routing networks that we develop essentially. To the carbon hub side, I'm thinking more as kind of Liz talked about, there's a lot of economies of scale to be taken advantage of. So looking at like pipeline routes, if you already have the existing infrastructure for these hard to abate sectors and you have those sources that are nearby, it's relatively it's easier, I would say, and maybe not as cost intensive to connect those nearby sources in those hubs, which means you can scale your pipeline sizes and get more CO2 and reduce that overall unit transportation costs because you're able to transport more CO2 than just from those hard to abate sectors. So hopefully that helps out a little bit.
Yeah, no, absolutely. I think so. And I think we're at a really critical point in time here where this system, we're just at the early stages of these technologies being deployed widely. So if we can, strategically begin to design some of these systems and potentially form these carbon hubs where it makes most sense, like where the geologic formations are, where we can take advantage of those locations. I think we could figure out how to take advantage as much as possible of those economies of scale, and even thinking through, oversizing some of those pipelines in spaces where we might need to, or where there are other industries that could connect pretty easily. So I think there's a big opportunity here.
Awesome. Okay. The next question is interesting because it frames things in sort of like an input-output way. Do you have any sense of the emissions and or life cycle impact of building out these networks relative to the amount of carbon they can transport and ultimately sequester?
It's a really, really great question. I mentioned at the end of this call that we've been thinking about understanding the amount of additional electricity that would be required to run a capture installation, and how that compares to the overall kind of grid. But in terms of comparing the emissions required and the resources, et cetera, required to build out a system relative to the emissions captured, I have not looked at that, but I think that's a very worthwhile question that should be investigated. Marcos, I don't know if at Carbon Solutions you all have thought about this at all. I know you have some LCA going on.
Yeah, no, I think that's a good question. We haven't done at Carbon Solutions and LCA specifically to look at, the emissions associated with the build out over the lifetime of storage. So I think that's a good question, and I want to be careful not to make sure opinion overrides like what I know for a fact we've done. I will say though that one of the other things that Carbon Solutions is doing kind of related to this is looking at what are the co-benefits from capturing CO2 emissions, because often when you're capturing CO2 emissions, there's a lot more that goes into it or is removed from emissions before it's released to the atmosphere. So I think that would be part of that assessment of the life cycle of emissions for CO2, because there's a lot of co-benefits from CO2 capture, which can benefit local communities potentially or the surrounding areas. And so I think we're already doing that at Carbon Solutions. So I think it would be kind of building upon that and looking at like the next step of the life cycle emissions, because I think that is a good question, a good point, and something that we have to keep in mind when talking about these.
Yeah. So I guess another interesting question for you. Can you talk to me a little bit about the energy and electricity infrastructure that would be associated with this?
Let's see. So each of these pieces will have some energy requirements. I think the capture piece, the capture installation, capture technology will have, depending on the technology, I should say. So I mentioned that we're looking into 3 different types at the moment, but each of them have additional energy requirements in order to run them. And so I know that in some of the other research that I do looking at the electricity grid, that even without adding these new sources on, there's just a increasing demand for electrification. And so you're seeing more and more kind of time lags between when folks are trying to request to add onto the grid versus when they're actually able to do it. I think there's been a median increase in the time for application on the electric grid of almost 5 years. And so I think that, in addition to all these other technologies and companies, industries that are trying to electrify now, to add the carbon capture system in there as well, I think is a concern for some because they're seeing that the infrastructure for the grid is not being built out at the rate that it might be needed in order to meet the, increasing demand for electricity. And so, that what sparked some of the initial research here is we are really interested in understanding what that will mean for these smaller grid locations. So for cement plants, for example, that are located in, these more remote areas in the US, what will that do to that grid to add a significant amount of electricity? So we're certainly interested in better understanding that. And Marcos, I don't know if you all have looked into this question as well and anything to comment there. But I know I'm excited to really jump in and understand the trade-offs here.
Yeah, I think the right answer is essentially it's something that people at Carbon Solutions have looked at, are looking at. I know it's something that is in our minds when we're doing some of this cost modeling, especially on the capture side of things, because you need a lot more electricity for running some of these capture systems. But in terms of specifics, I would not be the right person to answer that. But I can definitely connect people to the right people to answer it at Carbon Solutions. But I know it is something that we've thought about for sure.
Great, thank you.
Gotcha. Okay. Let's return to 45Q for a moment, and the sort of planning that would be required around the development and build out of carbon hubs. Do you think that existing 45Q incentives provide enough for the hubs to be built out, or does there need to be more regulatory input to guide development, perhaps across, multiple corporations, industries, with the end goal of the lowest system cost?
Yeah, I do think that this is a challenge. I think that, we have quantitatively showed that it can make a lot of sense, but I think that there's a lot of pieces that we need to sit down and work through. I mentioned even just getting some of the permitting for a single site location can take a very long time. So then when you think about that larger system, I think sitting down and working with the folks in DC on sitting down and understanding how to create incentives, how to look at some of the current regulations to really understand how fast can we begin to build these systems and can we do it in a very strategic way. I think that will be key. I think that the 45Q incentive will need to be increased. I showed numbers for cement today, but I've definitely looked at other industries, and I think their capture costs are also pretty significant. And especially when you look at some of the key characteristics that are not often included in those estimates. And then again, that doesn't account for the build out of a pipeline network, um, the build out of some of the storage sites. And so I think, yes, we'll need to work together. I think this is again a big opportunity to work with policymakers that are interested, with some of the researchers to run some of these scenarios and understand what could this future look like under these different mechanisms. So I hope that we can all work together to do that because I think there could be an opportunity to do so. All right, Marcos, I'm going to pass it over to you.
Thanks. Yeah, another great question. I think in terms of like working with regulation, I think Liz is completely spot on. In the past, just like from what I've heard and read, there's also the uncertainty around pipeline regulations, like who's controlling pipeline regulations specifically just for CO2 pipelines. And so I think there's a lot of unanswered questions that people are attempting to answer both like federally but also at local levels. I know there's a lot of new regulations and laws being passed around storage, subsurface rights, things like that. And so I think as there's more clarity provided by regulators, Liz is completely spot on where it's an opportunity for us to work with them, us being researchers, scientists, in the space to identify the right regulation to kind of help support and encourage this industry. And I'm not saying that from the perspective of like, hey, give us more money, more of just like, here's some more clarity and guidance on like regulations governing these things. And I think that that's happening, and that's really encouraging to me to see like, lawmakers making these regulations and then industry responding. And I see it as a really positive thing, and I think there's a lot more that needs to be done on that front, but I see us moving in that direction.
Okay, wonderful. So we're coming up to the end of our Q&A here, so I just wanted to give a couple more minutes for more seconds for any last questions. But in the meantime, Liz and Marcos, I did want to invite you to share any last thoughts if you had anything else you wanted to hit on that you didn't get a chance to, but we'll just take a couple seconds.
Yeah, I mean, for me, just would love to let everyone know that if anyone's interested in the work or has any questions, please feel free to reach out over email. Very happy to chat about it, and very open to new ideas. Like I said, the idea around estimating the emissions of building out the system and comparing that to what can be captured, I think that's a great idea and would love to investigate it. So welcome any other ideas that come up, or any opportunities for collaboration with any stakeholder that would like to engage.
Yeah, I'll echo what Liz said. I think this project's been really interesting for us, for a chance to kind of like do a gut check on capture costs for cement industry and things like that. And so I think projects like this are exciting for me as an opportunity to learn, to get better, to have a better understanding of the space that we're in, and the opportunities that exist. So I would echo Liz's sentiment of, people have questions, don't hesitate to reach out. This is always a chance for us to learn, grow, adapt. And I think this kind of work is what I find exciting and interesting, and trying to answer some big questions. So I always welcome the opportunity for more of that, essentially with Liz and the team, as well as with other people.